Kia ora and welcome back. In these first few videos, we've been going through some of the preliminary material you need to study abstract algebra. In this one, we're going to have a bit of a look through functions, defining what they are and some of the things that are important to know about them. Okay, so let's start by just thinking about or remembering these Cartesian products and relations that we talked about a little bit earlier when we were looking at equivalence relations. So a quick reminder, a Cartesian product of two sets, written A times B, is just the set of all ordered pairs where the first thing comes from the first set and the second element, B, comes from the second set, B. Okay, so that's what the Cartesian product is. Now when we take a subset of a Cartesian product, it's called a relation. So basically it's a collection of ordered pairs that's known as a relation. Okay, so we could, for example, if this is my two sets, I could illustrate a relation by drawing some lines which connect up ordered pairs. That would be a relation. Okay, we can use the same ones twice, doesn't matter. This would be an example of a relation. We've met one kind of relation before. We met equivalence relations. They are a type of relation where the set in question is the set, Cartesian product of the set with itself, and we defined a few extra properties that equivalence relations needed to have, but it's the same sense of the word relation that we're using here. Okay, so functions. Now we're probably quite used to functions from having studied calculus and things earlier on in our mathematical careers, but functions are actually a kind of relation as well. So a function is a relation where we have an input set which we call the domain, and we have an output set which we call the codomain. And just like before, just like with our relation picture before, a function assigns or a relation between these two sets. However, the important thing about a function is that there's only one line coming out of each element in my domain. So you notice that if I look at my set A here, all the elements, little a, b, and c, they all have a related element in B, and it's never the case that one element in A is going to two different things. As soon as that's happening, it's no longer a function. So that's sort of pictorially what a function actually is. Okay, so there's a little bit of notation that we need to use for our functions. So we could just write that our function is a subset of the Cartesian product of A with B, but that sort of reads a little bit strangely. We don't usually write it that way. Instead, with keeping in the back of our minds that this is what it actually means, we usually write that our function, we specify the sets, so we specify the domain, and we draw an arrow to show that the domain is A and the codomain is B. So that tells us what sets are involved, and then we can either go through each element and specify the rule. So we could say that f of A is equal to W, f of B is equal to Y, or we could say f of C is equal to V, or maybe there's some kind of formula, for example f of x equals x squared, that gets us from our domain into our codomain. The other notation that we will sometimes see is we might, instead of writing f of x equals x squared, we might write the function f takes in x and maps it to x squared. These are all notations that we'll see. Another common notation is we might write f of some set where S is a subset of our domain. All that means is it's just the set f of S is equal to the set of f of little s where little s is a member of our set. So it's just a nice shorthand for saying take everything in my subset S, apply the function to it, and collect the results into a set. Okay, so there's one more thing. So now that we have that notation, the range of the function is equal to just f of A, sometimes written as the range of f. So if we take all of our elements in our domain, apply the function to them, and collect them together, that gives us the range. So in our picture we've got up here, this part here would be the range of our function. So you can see that the range is contained inside the codomain. It can be equal to it, or it can be a proper subset of it. Both things can happen. Okay, so for example, if we were to look at a function on the real numbers, we could say that the function sine maps real numbers to real numbers. That's just using this notation here. So I've indicated the domain is the real numbers and the codomain is also the real numbers, but the range of sine, now it seems a bit weird to write it this way, but the range of sine is just equal to the interval -1 to 1, because we know that sine of any real number just goes between -1 and 1 and all the numbers in between. So that range is contained within the codomain, which was R. And I could have said that the codomain was -1, 1 interval if I'd wanted to instead. So long as it enclosed that range, then it would have been fine. Okay, so not just any old relation could be a function. We saw we've got that special rule that says I can't have multiple branches coming out of my function here. So what we say in that case is we say that the relation is well defined. So a well-defined relation, so this relation R is the subset of the Cartesian product A with B, is well-defined if every element A is mapped to a unique element in the codomain B. So let's just do a couple of examples just to show what that might look like. So here is an example of something that is not well-defined. So if this is my set A again, and this is B, and if it, for example, looked like this, that would not be well-defined because I've got two different assignments in B to this top point just here. So this one is not well-defined. Okay, it can go the other way though. So if I had a situation more like this one here, where I have these 2 points and maybe these 2 points, and this is A and B, if it looked like this, it's fine. I'm allowed to have multiple values in A mapping to the same value. That is a function. That is well-defined, but top one is not. Okay, so a function is just a well-defined relation. Okay, it seems kind of obvious that if I've got a function with a recipe like f of a equals something or other, that it kind of prescribes the output, and how could it possibly be that it could be assigned to two different values? But quite often in algebra, we have that the elements from our set A can be represented in more ways than one. And if the output depends on the way we've represented it, then we can have problems. So for example, if I set up a relation f which goes from the rational numbers onto the integers, defined by f of p over q is equal to p plus q. Now this is not a function. Let's see why. So if I were to calculate f of 1 over 2 of f of a half, then that would give me 1 plus 2, which is 3. Then if I do the same thing again for f of 2 over 4, that will give me 2 plus 4, which is 6. But the rational numbers, 1/2 and 2/4 are the same rational number, therefore I cannot have them both being mapped to different values. So this relation is not well defined, or it's ill-defined. Okay, so sometimes we may have to test for our functions being well defined if we have a function where the domain contains things that have multiple different ways of representing them. We have to make sure it doesn't depend on the way it's been written down. Okay, a little quick survey of some other properties of functions. Functions can be one-to-one and or onto. So a function is one-to-one if f of a equals f of b implies a equals b. What does that mean? Well, that means that it's one-to-one if I have two things with the same output. If that's the case, then they must be the same value. So a one-to-one function looks a bit like this first one here, because there's no two different values from A going to the same value in B. The second one, however, is not one-to-one, because I have got two things in A going to 1 in B. So this is 2-to-1. Now this definition, f of a equals f of b, implies a equals b. If we ever need to prove that something is one-to-one, we'll use this approach here. We start with this. We start by saying, assume f of a equals f of b, and then we'll do some work to show that a equals b. Okay, so that's the idea of one-to-one. Now onto is also known as surjective. A function is onto if for everything in the codomain there is something in the domain that maps to it. So when we're looking for a function being onto, we're going through B, and we're looking at all the elements and making sure that every element has something in A that maps to it. So the first one is onto, because everything in B has something in A that maps to it. The second one is not, because of this one here. There's nothing in A that's mapping to that point in B. Okay, another way of stating that a function is onto is to write that f of A, i.e. the range, is equal to the codomain. Now, we can also have functions that are one-to-one and onto. These are known as functions that are bijective, or they are bijections, or they are permutations. These are all different words for the same thing. So a function, let's rule out which ones are not. So this first one, it's got a 2-to-1 mapping here. So this one is not one-to-one, so we can rule that out. So to be a bijection, it has to be one-to-one and onto. So this is not one-to-one. The second one, in fact, it's not onto either. There is a point that doesn't have something mapped to it. So it's doubly not a bijection. Second one, it is one-to-one, but there is a point that's not being mapped to, so this one is not onto. So the third one is what a bijection looks like. It's one-to-one and it's onto. Every element is mapped to another element in the other set. And for finite sets, it also means that you've got the same number of elements, and it looks something like that. Everything is sort of in a nice correspondence. So we'll study permutations in a lot more depth a little bit later in the course, but it's just worth noting that permutation is another name for a one-to-one and onto function. Okay, so the last thing that I want to look at is composition. So when we've got functions, so let's say I've got two functions f and g, where f takes a to b and g takes b to c. Then the composition, which we write as g circle f, I'll explain why it's in reverse order in a second. It takes A from the first one and maps it to C, kind of through B as an intermediate, is given by the composition of G with F, G composed with F of X, is equal to G of F of X. So X goes into F first, and then the result of that goes into G. So if you were to draw a little picture, basically X goes through F and turns into F of X, which then goes into G and gets turned into G of f of x. And if we want to just illustrate which sets those came out of, so the result of that is in C, the result of that first one is in B, and our point x itself started in A, so our composition mapped from A into C directly in one hit. Okay, so that's kind of loosely speaking what composition is. When we compose two functions together, it gives us a new function which goes straight to the final set by passing the other two. The thing to remember is that even though f happens first, so x goes through f and then through g, we write it down in the opposite order because if you think of it in terms of this expression here, x is closest to f, so it goes into that first and then into g. Okay, we'll just finish off with a couple of facts about composition. So fun fact number one is that composition is associative. What does that mean? Well, that means if I have three functions, so now I've added in a third function h, then it doesn't matter whether I compose g and h first and then f, or whether I compose f and g first and then h, I should get the same result. So let's see if we can show why that's the fact, just sort of approximately. So f composed with g composed with h of x, that is written as f of g composed with h of x. So this is kind of my left hand side, is equal to that, which in turn it will be equal to f of g of h of x. Okay, but then that's actually the same as saying, let's have a look at the right hand side now, so it's show it's the same thing. Not really the cleanest way of proving this, but it will do the job. This time, if I were to do the right hand side, then I'll get f composed with g of h of x, so it equals that, which again will be f of g of the thing, which is equal to my right hand side. Okay, so we get the same result for both the left-hand side and the right-hand side. So typically when we write down multiple compositions, because it's associative, the order in which we bracket them doesn't matter, and so we'll tend to just write down without any parentheses at all, F composed with G composed with H. It's like how when you multiply three matrices together, it doesn't matter which order you do the evaluations in, you'll get the same result in the end. Okay, so fun fact number 2 is that if F and G are both one-to-one functions, then so is the composition. Okay, how does that work? So remember, if a function is one-to-one, it means that f of a equals f of b implies a equals b. So that's the fact that we want to make use of for this one-to-one function thing. Okay, so that means we're saying that if g composed with f, that's the function that we want to establish is one-to-one. So suppose, let's just make a bit more space. So we'll assume that g composed with f of a equals g composed with f of b, and we want to show that that implies that a equals b. So let's see if we just take the definition. So that means this implies that g of f of a is equal to g of f of b. But we know that g is one-to-one, and I've got g of thing 1 is equal to g of thing 2, and therefore f of a thing 1 must be equal to thing 2 because g is one-to-one. And then we'll therefore have that a equals b because f is one-to-one. And hence a composition is one-to-one. Okay, so this actually holds true for Onetooness as well. We're not going to prove that, but we can just summarize these facts into a theorem. So the first one is the theorem about composition being associative that we just did. We just proved that. We just did if f and g are both one-to-one, then so is the composition. So it turns out, and I'll let you have a go at proving this yourself if you fancy it, that if f and g are both onto, therefore so is g composed with f. And also, following from 2 and 3, if that's one-to-one and onto, it also means that it's going to be bijective as well. So if f and g are both one-to-one and onto, then g composed with f will be both one-to-one and onto, and therefore g composed with f will also be a bijection. Okay, so that was our whistle-stop tour through functions. We'll be using some of these ideas a little bit later on, but it's worth just keeping these here as a reference. So we'll see you in the next video. Ka kite anō.